In solvent-based automotive coatings, particularly in clear coats and primers, solvent release and cure are tightly coupled processes that profoundly influence the development of residual stress and, ultimately, long-term performance. Understanding these interactions is essential for translating laboratory success into robust, OEM-approved production coatings. Solvent release begins immediately after spray application. The film contains a mixture of low dash, medium dash, and high boiling solvents, which dictate the evaporation profile. Rapid solvent loss at the surface can form a skin that impedes deeper solvent diffusion, while slow solvent release prolongs film openness, allowing continued flow and leveling. The balance of evaporation rates is critical to avoid defects, such as solvent popping, pinholing, or micro-void formation. Curing reactions, whether cross-linking in a clear coat or primer, begin as the solvent content decreases and reactive species come into proximity. Solvent evaporation influences cure kinetics. Too rapid evaporation increases viscosity prematurely, restricting cross-linking mobility and potentially creating incomplete cure zones. Too slow solvent release delays network formation, leaving the film soft and prone to flow-induced defects or sagging. The interplay between solvent release and cure generates residual stresses within the coating. Residual stress arises from constrained shrinkage, thermal gradients during bake, and differential cure across film thickness. High residual stress manifests as microcracking, adhesion loss, or premature gloss reduction, while low residual stress can compromise mechanical integrity, such as stone chip resistance. Film thickness variation magnifies this effect. Thicker films retain solvent longer, potentially undercured at the core, while surface layers are fully cross-linked, creating a stress gradient. Thin films may cure rapidly with minimal residual stress, but sacrifice mechanical robustness. Correct DFT and solvent balance are therefore crucial to minimize stress accumulation. Laboratory versus production behavior often diverges. Lab panels are thin, flat, and thermally uniform, allowing controlled evaporation and cure. Production car bodies introduce complex geometries, varying thermal mass, uneven airflow, and local environmental differences. These factors create spatial variations in solvent release and cure, leading to localized residual stresses that may cause orange peel, microcracking, or adhesion variation in production. OEM durability validation evaluates coatings under accelerated weathering, thermal cycling, chemical exposure, and mechanical stress. Residual stresses influence performance in each of these tests. Coatings engineered for robust solvent-cure balance maintain dimensional stability, adhesion, and appearance throughout their service life, even under fluctuating process conditions. From an RD&I perspective, designing coatings requires an integrated approach. Solvent package engineering to control release profiles, rheology and resin architecture to support controlled network formation, process optimization to account for bake profile, airflow, and part geometry. By managing solvent release, curing kinetics, and residual stress development in tandem, coatings teams ensure appearance, mechanical durability, and OEM approval reliability. In summary, solvent release, curing, and residual stress are interdependent processes that govern long-term coating performance. Laboratory evaluation alone cannot capture production variability, making system-level design essential for robust, OEM-compliant coatings. If you have technical questions related to residual stress control, solvent-cure balance, baking optimization, or lab-to-line discrepancies, share them in the comments for future discussion in this masterclass series.